In this video, I'm going to be giving you hints and tips as to how to start each of the questions on Edexcel's AS Sample Assessment Materials Paper 2. Now, Paper 2 of the AS exams are split up into two parts, statistics and then mechanics. We're going to start at the start, obviously, with statistics. Each of the questions in this video, because some of them are quite wordy, I'm just going to assume that you have read them through yourself instead of me reading them through. If you haven't at any stage, just pause it and read it through yourself first. This first question is an investigation that Sarah's doing with a large data set, and we're first asked to state the sampling technique that Sarah used. There are only a limited number of sampling techniques that you're expected to know at AS, and they are neatly summarised in your Pearson textbook at the end of the first chapter here on the right, those sampling techniques there. So I'll leave that to you to go and look those up and pick the correct one for this question. Part B is referring to your knowledge of the large data set. Your knowledge of the large data set may or may not be there right now. Hopefully, through the course, you'll gain some familiarity with the large data set. There are some summary sheets that point out some major things about the large data set that we will revise as well at some point. But if you come across a question and you have no idea what's going on, you can often make a really good guess as to what the question wants. In this case, why might this sample not generate a sample size of 20? Just imagine a list of data and imagine doing the sampling that Sarah uses as described there, and just have a good think about why it might not get 20 results in total. And write that down and cross fingers, you'll get a mark for it. Ideally, you'd have the knowledge of the large data set, but if you don't, make a good guess. Part C is more of a standard stats question. We've got some summary data. We've got the number of data points. We've got the total, and we've got the total of the squared values. And we need to put those together to make the standard deviation. You might want to refer to the formula book, because in the AS bit of the formula book, we are given formula for the standard deviation there. It's the square root of the mean of the squares minus the square of the mean. Mean of the squares minus the square of the mean. Mean of the squares minus the square of the mean. Right, and that's it for question 1. Question 2. I really like this question because it's just like a bit of a puzzle. A couple of things about histograms first. Remember that in a histogram, the area equals the frequency. So the area of the bar, area of each bar gives the frequency within that bar. And that is why frequency density is labelled up the side instead of frequency. Also, a funny thing about this question in particular is this sentence here, to the nearest minute. And so, for example, when 4 to 6 minutes is labelled there, that refers to the first bar, even though the first bar is between 3.5 and 6.5, because they're all the values that would be rounded to 4 or 6. Now, why is it like a puzzle? Because we've got to use this information to find how to label the frequency density up the side. Then we use the information that's here to fill in the missing values in the table. And then we use the values in the table to figure out what we actually need. That sort of going back and forth, I think, is quite nice. Hopefully you'll enjoy it as much as I did. Question 3, a nice Venn diagrams question. This, find the value of P first. Note that it's worth 1 mark, and so it should be fairly simple. Just one line of working using the Venn diagram and using this value here, just to find the value of P. Part B states whether A and T is statistically independent. I'll remind you that independent means that the probability of A and T happening at the same time is the probability of A times the probability of T. As before, if you need more practice with that, you can look it up in the textbook, but that's what you need to use there. And the probability of a student selected at random does not take part in athletics or cricket. I'll leave that to you. That's just picking information out of the Venn diagram. Question 4. This one looks a bit chunkier. Another reference to the large data set here. We've got some data and we've got some information about the quartiles. Quick note about quartiles here. I like to always imagine them on the box plot that you could draw from them. So the lower quartile, Q1, the median, Q2, and the upper quartile, Q3. Just have that image of a box plot in your head. I think it's quite nice. We're asked to show that 20.6 is an outlier by calculating the interquartile range, the difference between the upper quartile and the lower quartile, and doing a little calculation with it and showing that R is outside it. You can do that. Give a reason why Sarah might include or exclude an outlier. Now, your answers to those could be a little bit fluffy. By fluffy, I mean just write down what you think and you'll probably get the mark. There's no advanced mathematics in that question. Just why might you include an outlier? Why might you exclude an outlier in a succinct sentence? This next one about interpreting the correlation shown in this scatter diagram. I think I mentioned this in paper 1. I know I mentioned it in paper 1. That whenever you see the word interpret in a maths exam, it means that you need to refer to the real life context. So in your answer to this, you need to give some explanation as to what it shows about rainfall and humidity. You need to mention both of those words. That comes up in part D again, when we're asked to interpret the gradient of this regression line. Say specifically what that 0.15 means for the humidity and the rainfall. Like, if humidity goes up by a certain amount, then how much does rainfall go up? That sort of interpretation. Part E, comment to the suitability of Sarah's sampling method and how she could make better use. That's another, well, part 1 of that, as I mentioned before, write what you think. Don't worry about it being extra mathematical and then checking the mark scheme as to whether it's all right. Cross things it will be. You get better at these sort of questions with practice as to what the mark schemes say. And suggest how Sarah could make better use of the large data set. Similarly, have a guess and check what the mark scheme says and learn from that for the future. Part 5 is back to a standard binomial question, hypothesis testing question. We've got part A is plug it into your calculator, but be careful. Remember that your calculator gives less than or equal to certain values, and we're asked for the greater than or equal to. So if we've got this binomial, remember that binomials we can imagine being like little bar charts, the probability of each being vertically. And we're asked for greater than or equal to 16. Suppose it's up there. Have a think about what the opposite of that will be. Less than or equal to what if 16 was that bar there? Next is hypothesis testing, but kindly, they've split it up into different parts to remind you how to do hypothesis testing. You'd be very kind here. So for part B, you've got to write down H0 and H1. And part C, you've got to find the critical region. This one about the critical region, state the probability of rejection in each tail. I'm going to draw out my little bar chart again. Remember that if we have a certain significance level, in this case 10%, because it's a two-tailed test, we're separating it into 5% up that end and 5% down that end. But the actual probabilities that come out of the binomial thing when you do it on your calculator won't be exactly 5%. We're looking down here, for example, for the first, for before it goes over 5%, we need that green bit down there to be less than 5%. And the actual probability of rejection in each tail is the actual probability of being down there in that green bit in this case. And then you've got to do the same at the other end. And the actual significance level is just those two things added together. Then part E is using what we found, interpreting that 12 in the context of your critical regions, and then something else about why the model might not be valid in this case. And you've got to think back to when you did introduction to the binomial distribution, what assumptions we have to make in order to model something as a binomial random variable. Again, that will be in your textbook if you've forgotten. We're on to mechanics now. Another one of my favourite questions here, this first one, because we're asked to look at a graph and derive a Suvat equation. It says we're not allowed to use Suvat equations from the formula book. We've got to derive them. And the biggest thing that you need to remember on this question is that if we're given a velocity time graph, then the area underneath it, area under the graph, which you could interpret as the integral between 2 points, because the integral gives the area under the graph. The area under the graph gives us the distance travelled. Yeah, I think it's positive. There's like whether it's distance or displacement, that is not necessary here. But if it goes below, then there's something funny happens. But in this case, when it's just all positive, it's nice and neat. The area under the graph is the distance travelled, and you can use that to derive the equation necessary. Question 7. Car moving along a horizontal road, and we're asked to find accelerations and speeds. With a lump of text like this, I want to do a sketch to get it okay in my own head. A sketch that you might start off with might just be a section of road, and you've marked, well, that's a road there, and you mark on A, B, and C, and just label on the information on that sketch just to get it okay in your own head. Perhaps a then useful sketch after that, I'm thinking if we've got a constant acceleration, then if we were to sketch a velocity time graph, similar to the last question, then the graph will be a straight line, because the gradient of a velocity time graph is acceleration. And you can label information on that sketch graph and use that to answer the question. Interpret it on the graph. Next. Question 8. Ooh, a bird. A bird leaves its nest at time t equals 0. I'm going to imagine that the nest is in a tree, and the bird leaves the nest and goes in a straight line away and then back again. But its distance isn't just there and back, its distance is dictated by this expression here. Explain the restriction, that restriction there. 3 marks seems quite a lot for this. Try to figure out why it can't go outside of that restriction. So why can't time be negative? That one's pretty easy. And why can't, in this case, time go greater than 10? And you can get that okay in your head by just plugging in a value that's greater than 10. So pick a value 11 and plug that into that expression, and maybe that'll lead you to the answer. Part B, find the distance of the bird when it first comes to instantaneous rest. Instantaneous rest, what does that mean? If we plot that on a graph, that would mean, so in this case, a distance time graph. Instantaneous rest means it's a point where it's stationary, but not necessarily stationary for any length of time. So you might interpret it that as when the bird goes out and the point at which it turns back. Because if its velocity is going from positive to negative, then it must be zero at some point in between. On the graph, it's where the graph has gradient 0. So I spoke about word associations in paper 1. Instantaneous rest, to me, immediately makes me think that the gradient is 0, the velocity is 0, that in this case we've got s and t, ds by dt equals 0. Get that association in your head as well. Question 9, a classic connected particles question. We've got two masses on pulleys, two masses connected over a pulley. And we're asked to write down equations of motion. I would start by labelling on, we've got loads of information here about forces and whatnot, labelling it on this diagram. Then, if you want more help from there, I like to label out the diagrams separately. And often in connected particles diagrams, connected particles questions, there are 3 diagrams that you can draw. We've got A on its own, and all of the forces that are acting on A. We've got B on its own, and all of the forces that are acting on B. And then the third diagram is imagining that A and B were stuck together and all the forces that are on both of them. For the first two, tension will play a part. I think A, tension will be going this way, and B, tension will be going upwards. But for A, B together, imagining that just being a whole chunk that's being pulled around, you'll have to imagine that it's like the string is straightened out and it's just being pulled left or right rather than going over the table. Tension won't come into the third one. All of those diagrams will have exactly the same acceleration. That's the thing that carries over between the diagrams. And when you come to using Newton's second law, remember that in F equals ma, F stands for resultant force. So do all the diagrams first, find the resultant force in a certain direction, and then apply F equals ma. Only apply it after you've found the resultant force. Part C is using the model to find the time it takes from release for B to reach the floor. I reckon SUVAT will come in there. Once you've got acceleration and we're talking about time and distance and velocity and whatnot, you're going to be using SUVAT, and you're going to lay out your SUVAT very nicely, aren't you? Writing everything out neatly and picking the correct SUVAT equation from the formula book. And D suggests 2 improvements that could be made in the model. Classic interpretation question at the end of these things about why our model, especially these assumptions in this paragraph, why they might not actually apply in real life. And it's 2 marks, 2 improvements that could be made. And I think that's the end of the paper. So good luck with all of those yourself, and as before, persevere with them. Have fun.